So here's a practice problem for buffers that we typically see. So here's the question, and the question says, calculate the pH of a buffer composed of 0.10 molar acetic acid and 0.10 molar sodium acetate. And you're given the value of Ka, which in this case is 1.8 times 10 to the minus 5 for acetic acid. And so when you look at this type of question, the first thing you want to do is you want to make sure you know what the equation is. So here, for example, we have acetic acid reacts with water, and it's an equilibrium reaction. We produce hydronium ion because, of course, this is an acid. And then we have acetate here, and acetate differs by one hydrogen or by one proton relative to acetic acid. And so this is the conjugate base. So if we were going to make a buffer, we would want a weak acid, acetic acid, and we would want its conjugate base, which is acetate. And the source of acetate is sodium acetate, because once you put sodium acetate in water, it's going to produce acetate. So the next thing, anytime we talk about these, what we always want to do is we want to do an ice table. So the initial concentration of acetic acid is given to us, 0.10 molar. The initial concentration of hydronium ion is approximately equal to 0. Of course, this is going to be an assumption that we're going to talk about in a minute. And then the concentration of acetate comes from the sodium acetate. And because sodium acetate dissociates into acetate, this is the concentration, 0.10 molar of acetate. And so what's the change that happens? Well, the change is we get a negative X change, and because these are all one-to-one relationships, the concentration of hydronium ion increases by plus X, the other product, acetate, increases by plus X when we get to equilibrium. And so when we get to equilibrium, the equilibrium concentrations of acetic acid are 0.10 minus X, the concentration of hydronium ion is plus X, and the concentration of acetate ion is 0.1 plus X. And so what we also need to do is we need to talk about the fact that there are going to be some assumptions. The first assumption is, of course, that hydronium ion at the beginning, in the initial hydronium ion, before anything has happened, is approximately 0, because the auto-ionization of water produces some hydronium ion, but we're going to say this is negligible. And the second assumption is that X is going to be very small, and we can say this because Ka is very small. In fact, it's 1.8 times 10 to the minus 5. That's very small, Ka. And so Ka is going to be very small relative to the initial concentration. So 0.1 minus a very small number is still going to be equal to 0.10. And so that's how we're going to make this assumption. We're also going to say that 0.10 plus a very small value of X means that this value is going to be equal to 0.10 as well. And so if we now take our Ka expression, hydronium ion concentration multiplied by the acetate ion concentration divided by acetic acid concentration, we can plug these numbers in. And so hydronium ion is X, acetate is going to be plus 1, is going to be 0.10, and because we're making this assumption that X is small, this value is 0.10, and it's going to be divided by the concentration of acetic acid, and we've made this assumption that acetic acid, the concentration of acetic acid at equilibrium, is going to be approximately equal to that at the beginning. And so what if we do some algebra, we end up with the concentration of X equals 1.8 times 10 to the minus 5. And so because X is the concentration of hydronium ion, which is X, then the concentration of hydronium ion is 1.8 times 10 to the minus 5. And what we're asked for is, well, what's the pH of this buffer solution? And we know by definition that pH equals minus log to the base 10 of hydronium ion. We plug hydronium ion in here, we end up with a pH of 4.7. And so we should always check our assumption, and our assumption is, of course, that the value of X, which we said was going to be very small, small meaning it's less than 5% of the initial concentration of acetic acid. So if we take the value of x and we divide it by the concentration of acetic acid at the beginning, the initial value, multiplied by 100, we end up with 0.18%. And 0.18 is certainly much less than 0.5%. So our assumption is valid. And because our assumption is valid, we can say this is what the pH of the solution would be. So ice tables are extremely helpful and are able to give us a lot of information and are very good to practice with. And several of the questions we use ice tables for. Now, out of interest, if you've been reading ahead in your textbook, you'll realize that there is another way that we can do these types of questions. And that's if we look at this question again, and later on we're going to talk about what's called the Henderson-Hasselbalch equation. And what this does is it relates the pH to the pKa and the concentrations of, in this case, the conjugate base divided by the acid, the weak acid. And in this particular case, we could use this equation to calculate the pH of this buffer. And so we're given Ka, and we're given Ka. What we actually need is we need pKa. So the definition of pKa is minus log to the base 10 of the equilibrium constant. So we could take this value and we could put it into our equation, and pKa would then be minus log of 1.8 times 10 to the minus 5, which give us a value of pKa of 4.7. So now we would have this value here, and the concentration of the conjugate base, which is acetate, we're also given that value here, 0.1, and the concentration of acetic acid, which is 0.10 molar as well. So what we could actually do is we could take these values, we could add the pKa value into the equation, and then we add the log, and all of it is the log of 0.1, which is the concentration of the conjugate base over the acid. And if we calculate this, the log of these two cancel out and you end up with a log of 1, which is 0, and the pH is 4.0. So a much shorter way of doing this this particular problem, but not every problem can be use the Henderson-Hasselbalch equation. So it's well worth knowing how to do this with ice tables. But then when the chance comes, you can of course use this equation, which is really extremely helpful for us to be able to understand what the pH of buffer systems can be.